In our everyday lives, electromechanical machines play a major role in the way we live. They have become an integral part of our modern civilization. Imagine the way our ancestors lived without cars or planes that take us from one place to another, or tractors to till the soil, or the pumps to bring water to our faucets, or even the simple lawnmower to cut the grass in our backyards.
We cannot think of a life without all these machines that we take for granted today. What is common in most of these machines is that they generate force to move things around using mechanical arms. Such arms can cause translation or rotation, or a combination of both.
Either way, the machines need to generate force so that the arms can do the job, just like our muscles generate force to lift a weight. Micro machines also need force so that their little arms can do the work for us. There are various ways to generate force. Here we will explore 3 such ways, and how they change as size becomes smaller and smaller.
Let us first consider electrostatic force. You know that opposite charges attract each other. The force between 2 charges decreases as the distance between them increases. If the distance is halved, the force increases by 4 times. That is, the force is inversely proportional to the square of the distance.
Now consider 2 parallel metal plates, one carrying positive charges and the other carrying negative charges. You can accumulate such charges by connecting the plates to the poles of a battery, which produces a fixed voltage between the plates. Electrostatic fields develop between the plates and around them as shown by the white lines. The opposite charges attract each other and a force is generated between the plates.
How does the force scale with size? For a fixed voltage, the force is inversely proportional to the square of the gap between the plates. If the gap is halved, the force increases by 4 times. Now, if the plate size is reduced, the amount of charge that you can accumulate in each plate also reduces proportional to the area of the plates. Just as the amount of water that you can store in 2 tanks with the same height depends on the floor area of the tanks.
The area of the metal plates carrying the charges is proportional to the square of their sides. If the size is halved, the area reduces by 4 times. Thus, the force between the plates reduces by 4 times as well. So the force increases as the gap is reduced, but decreases as the plate size is decreased.
If the 2-plate system is now scaled down in size by reducing the plate size and the gap, then the force does not change at all and the force becomes independent of scaling. Mathematically, the force is proportional to length to the power 0 when the voltage between the plates is kept fixed.
To put the scaling into perspective, recall that the weight of an object decreases as the cube of its size, and the stiffness of a spring decreases as the size itself. If the size is halved, weight decreases by 8 times, but spring stiffness decreases by 2 times. In contrast, electrostatic force between the plates does not decrease at all. Electrostatic force becomes the dominant force at small scale, and is a popular means of generating force for MEMS devices.
Here, a voltage is applied between the cantilever and an electrode on the right side. Electrostatic force develops between the electrode and the cantilever. The cantilever is pulled towards the right, but instead of a constant voltage, the voltage fluctuates with time, which generates a fluctuating force and the cantilever resonates.
Here, 2 microbeams are buckled by electrostatic force generated in a MEMS actuator. They are 500 micrometers long, 10 micrometers tall, and 1 micrometer wide, 100 times smaller than a human hair. In Sandia National Laboratory, electrostatic actuators are used to turn little gears and move a small mirror.
Now let us see how magnetic force scales with size. As you know, similar poles of two magnets repel each other, and opposite poles attract. The Earth's magnetic north pole attracts the south pole of the magnetic needle of a compass, one of the early instruments for navigation.
In this animation, similar poles of two magnets are brought close to each other. They feel a repulsive force between them. The magnetic field lines from similar poles stay away from each other. We can also make a magnet from a solenoid coil by running current through the wires of the coil. Magnetic force develops between the solenoid and the magnet.
Many rotary machines operate by generating force between a solenoid and permanent magnets. If we now scale our solenoid in the video to a smaller one, that is, reduce the length and the diameter of the coil as well as the diameter of its wire, as if we are zooming out, then the force that the solenoid feels reduces as size cubed.
If you reduce the size by 2, the force reduces by 8 times. Here we assume that the permanent magnet does not change size. In other words, the magnetic field strength due to the permanent magnet remains constant. We also assume that the current density through the wire of the solenoid, or the current per unit cross-sectional area, is constant.
So, the magnetic force scales as the weight due to gravity. The force decreases rapidly as the size is decreased, or conversely, the force increases very rapidly as the size is increased. Hence, magnetic force is popular for many macroscopic machines.
The choice of the type of force in MEMS not only depends on the way the force scales, but also how convenient it is to use for a specific application. Here, microflaps are moved by magnetic forces.
The flaps are about 1,000 micrometers in size. Each has a coil that works as a solenoid. When current runs through the coil, magnetic force is developed between the flap and an external permanent magnet. The force tilts the flap about a hinge. In the future, such flaps may be used to control the lift and drag of aircrafts.
Another source of force that might be useful for MEMS is the force of light. When light shines on a surface, it applies a small force on the surface due to the impact of its photons. If all the incident light is reflected by the surface, then the force is maximum. It is given by 2 times the power of light divided by the speed of light.
For most macroscopic applications, the force is too small to be very useful. Since MEMS devices need small forces, the light force may be sufficient. We will show you an experiment where light is used to switch the state of a buckled beam.
The idea is simple. Take a long slender beam, such as a ruler, and compress it to buckle. Then you can apply a force at the middle of the beam to switch its state from one buckled configuration to another.
We have done the same experiment at microscale. Here, 2 parallel MEMS beams are first buckled by a MEMS electrostatic actuator. Each beam is 1 millimeter long, 1 micrometer wide, and 15 micrometers tall. They are connected at the middle by a frame so that they can buckle together.
In the video, you see a zoomed-in view of beams near the middle. From the vernier marks, you can see that the beams are buckled towards the right. We shine a laser beam near the middle of the beams for a short time, which appears as a flash. You can see that the beams switch their state from right to left due to the force of light. Such buckled beams may be used as memory elements in the future for high-temperature applications. The use of light force for MEMS devices is currently under research.
To summarize, electrostatic force does not change with size, making it useful for MEMS devices. Magnetic force does change with size, making it better suited to macro machines. We have seen several examples of MEMS devices that are moved by electrostatic, magnetic, and light forces.
In the macro world, we can see what the large machines can do for us with the use of force, but we may not see with our naked eyes the activities of the micromachines. But sure enough, the use of various forces, both large and micromachines, have and will continue to shape our civilizations and our way of living in a profound way.